All right. So second presentation is Azimuth. And presenting to you guys will be Gabrielle Gauthier-Melançon, Senior Applied Scientist. I don't know what the titles are anymore at ServiceNow. And Orlando Marquez, who's a Staff Applied Scientist at ServiceNow. So take it away, guys.
Okay, well, thank you very much for the invitation, Matt and Alex. We're going to try something a little different today. I'm going to be giving you an intro. I'll motivate the problem, and I'll motivate our approach. But we'll do a live demo in sort of sketch mode. So we'll see if that works. Bear with us if it looks a little funny. Oh, that's the point. Okay, so let me motivate why we did all this work with a little anecdote, which comes from actual real life. So at ServiceNow, we have to ship models, we have to ship pipelines, but besides that, we also have to do some support. Now, of course, doing support might not be the funnest thing when you want to code or you want to run experiments, but it's actually very, very insightful. And although I didn't want to do it in the beginning, I then appreciated why we should do it. So this comes from a customer issue that happened to us maybe a year ago or so. We have an intent classification model, not very complex, a simple intent classification model that is supposed to predict intents based on some sort of IT ticket. So we are kind of like the lowest level of support. First, you're going to get someone who's general, and then someone else. And at the end, when nobody can answer, they come to us, scientists or engineers. So the customer had this complaint that when they had this utterance, I'm no longer able to print from my computer. They got what they thought was the good intent printer issue. But then, when they had another utterance, I'm no longer able to print from my laptop, they got a different intent, which is troubleshoot slow computer. And of course, they ask the question, why? Why is your NLP model giving me something different when obviously computer and a laptop are fundamentally the same thing? Semantically, they are the same thing. And then we got the customer support person coming to us and be like, okay, this person is very insistent. They want to know. We have to give them an answer. And they come to us and they're like, I don't know, really? I can make something up. But we do not know why machine learning models make predictions the way they do. It's probabilistic, and we need better tooling. So the answer was, I don't know, not very convincing. And so that motivated us to, well, we got to do some work on this. So if you have shipped software engineering code, traditionally speaking, before ML became so popular, you had, of course, all kinds of bugs, all kinds of problems, seg faults, which we always hated. You didn't know why it was happening, out-of-memory errors, index out of bounds, whatever you want. But with a lot of pain and effort, you could trace that back to some piece of code, right? You use tools, debuggers, use whatever you want. You could profilers. You could find something in the code with a lot of pain, and you could change it. Not easy, but you could trace it back to code. Now, in machine learning, if your model gives you a wrong prediction, if it's biased, if it hallucinates when it's generating text, like in summarization, where is the problem? Where is the error? You can have hypotheses. You can speculate. You can say, oh, it's auto distribution. Therefore, that's why I make a mistake. You can say, we need more data. Let's use data augmentation. Maybe it's going to help. Who knows? Or we have annotation artifacts, which I will explain in a little bit. Or we're overfitting. And it sounds very fancy, but really, we don't really know why models behave the way they are most of the time. But we should know, or we should try to know. So we are responsible as engineers, as scientists, for making sure, or trying to make sure, that our models behave correctly, ethically, responsibly. If you don't know what the Montreal Declaration for Responsible Development of AI is, you should take a look at it. It was done in this city under, of course, someone like Joshua Benyu with a lot of authority. But in 2018, they wrote this big document with many signatories, which is actually very, very important for us as science engineers. And part of it says, as you can read, that doesn't matter if your system is for sale or open source. An AI system should meet strict reliability, security, and integrity requirements. Now, it should be tested so that it doesn't put people's lives in danger. It doesn't harm people's life. Why? Because people rely on these systems to make decisions. So just to say, look, it's hard to find a source of error, is not good enough. It doesn't cut it. However, though, we lack tooling and we lack an approach. So that's the motivation for doing all this work. Now, people do, of course, some sort of error analysis. People do look at metrics, and we're going to give you the reason why we think it's not enough. But normally people, they create their data, analyze it, tune their models. We have great tools for that, transformers, we have rate tune, we have great stuff for that. But then we get into error analysis, and there's some stuff like NLP Interpret, Google Slit, Robustness Gym by Salesforce. Everyone has their own little tooling, but it's not systematized. And then you deploy. Now, if you have done error analysis, you probably follow something like this. Well, you look at metrics, right? And this could be model metrics, precision, recall, F1, as the speaker showed before. And you might even go further and look at calibration metrics, like expected calibration error, EC. You may have your own business metrics, which is good. But we feel that's not enough. That's just the beginning of quality assessment. Now, people who want to go further will look at their predictions one by one or in some form, use something like a Jupyter notebook, where they write their own custom thing, they look at Excel files with the predictions, some JSON output, and they try to make something out of it. But it's not very easy, it's not very systematic. So what has happened at the end is that practitioners either do it very quickly or they skip it, right? Because it's tedious work, it's ad hoc, it's informal. So we want to change that. And we propose this approach to address that, in which we try to systematize error analysis. So here it is, and we're going to go through it in concrete form in the demo, but I'm going to give you a little bit of context so that it doesn't feel foreign to you. So in the beginning, of course, we have inputs, data sets, and the models that you're going to analyze. Data set analysis, I'm going to go through it in detail a little soon. We have sort of 4 quadrants, 4 dimensions, and then model quality assessment to then look at the model. Now, you, of course, can do data set analysis without a model, and you should do it before you actually start modeling. But we feel it's part of a process that is iterative. And at the end, the outcome of this approach should be, well, you have good enough quality that you can train and evaluate on, and you have identified the failure modes that your model suffers from, either because you decide to ship or not ship, or you ship and you say, well, I have to address this, if not now, later. So you want to have good enough data and identify your model's failure modes. So if we go into the data analysis portion, we kind of group this into 4 quadrants. So data set shift is a common problem in ML pipelines. What is that? Well, you might train on some data, on training data, that has some distribution, and then you're going to actually deploy on a different distribution of related or similar data. And you want to catch that before you deploy your model. So ideally, your validation set or your evaluation set reflects that. And you want to catch that before you even start modeling. Class imbalance is very, very obvious, right? You want to make sure that if there is class imbalance, you quantify it, you address it as much as possible. Data augmentation, oversampling, downsampling, many techniques to do that. Class definition, what does that mean? Well, it's very hard to create data sets. If you take this from academia, you kind of assume they're good, although, of course, some of them have very, very good problems, no problems. But if you have to create a data set in production that is going to be used for a real-life system, well, you cannot assume that the classes are well-defined. Now, this applies to any task, although here we're talking about text classification. So what can happen if your classes are not well-defined? You have something like class overlap, right? Where 2 intents are very similar, and they were defined that way, and then your model gets confused. So they're not easy to separate. So if you don't catch that before you start modeling, or you don't address that, you might run into that problem in production. And lastly, we have problematic samples. Now, this is an area that is very hard to find at a data set level. For example, you might have examples from a different language, or examples that are atypical, maybe are too long for the task you're trying to solve, or they're too short. So you should try to also find out what do you have that in your data set and address it before you start modeling. Now, once your data set is analyzed, then we get into analyzing the quality of the model. Again, we broke that down into 4 quadrants. First is data subpopulations. What does that mean? You can calculate metrics such as precision recall or F1 on the entire data set. But that only reveals part of the issue, right? So for example, what if your data set has some characteristics in which your model actually fails? It can be, like I said, maybe long text. And your model really suffers when it sees long text. So you want to quantify its quality on that subpopulation. Annotation artifacts. Well, what's an annotation artifact? There are patterns in your training data that your model exploits to, instead of learning the task, it learns heuristics. The example that everyone knows is between classifying, say, dogs and wolves, in which the classifier learns that when there is snow in the background, they predict wolf, but they're not learning the task. They're not learning to differentiate between dogs and wolves, really. They're just learning to map snow to wolf. So that's an annotation artifact that you want to discover before you ship the model. Then we have robustness testing. Now, those who know NLP know that Ribeiro and colleagues changed the way we test NLP by introducing checklists. This paradigm to assess the linguistic capabilities of your NLP systems. So for example, you want to make sure that if your model sees the same example, but it has been slightly changed, for example, there's a typo, or you're introducing some neutral word, well, you don't want your model to change its prediction. So that's a robustness invariance test, which we have in our tool. And there are many, many other capabilities that one should test. Lastly, we have something we call uncertainty-based analysis. What that means is that there are some areas of your distribution that perhaps your model is unsure about. Perhaps because they're more difficult. And you want to be able to detect that before you ship your model. So for example, you should look at your perhaps lower confidence predictions and see why is the model being not so confident on these examples. Are they more difficult? Or if you have something like dropout, a very well-known technique to avoid overfitting, well, you can use Bayesian deep ensembles to find examples with high epistemic uncertainty and see why are those examples so difficult. Now, we're going to show how this is applied in practice through a demo. I just wanted to give you an overview. So let's get more concrete. Gabrielle is going to run the demo, hopefully, if the web cooperates.
Of course.
Okay. So, Gabrielle, I know I gave you a model. It's trained on the intent classification Clink dataset that some of you might be aware about. It's just a classification dataset where the examples are utterances that map to intent. It has 150 classes, and the model I gave you, to me, is very good. It's 90% accurate, right? And I want to use Azimuth to find out whether my model is actually good and my data is good. So what can you tell me about, say, let's start with the data, right? So data shift, as I said, I want to make sure that my training set and my validation set follow the same distribution. How can Azimuth help me find this out?
Perfect, let's start. So in terms of dataset shift, there's many types of dataset shift, so I'm just going to present one here. And it's about a shift in the length of the utterances between your training set and your evaluation set. So here we look at this distribution across all classes, and we can see actually there's not so much of a problem here. Sometimes you do see a shift. Sometimes the evaluation set, the sentences tend to be longer because potentially it's raw data and it's a bit more noisy. But here we don't see that problem. However, we do have 7 classes where there's a shift, a bit of a shift. So the evaluation set is a bit longer than, the utterances are a bit longer than in the training set, but it's not much of a problem.
Okay, so I should probably keep that into account. What about class imbalance? Is there any class imbalance on my data set?
So you did use the imbalanced training set of Clink, so we do see some imbalance in here. In the evaluation set, there's about 20 samples per class in all classes except the out of sample, which has 100 examples. And in the training set, most classes have between 50 and 100 samples, except 30 of them, which only have 25. So that might be problematic.
Okay, cool, thank you. How about, I want to make sure that my classes are well defined, right? I took them from the web. People have put effort into this data set. Can you tell me something about the class definition?
Yes, this is a harder problem to talk about. So I'll spend a bit more time on it. So there's 150 classes, right? So it's a bit hard to assess if each class is well defined. But in Azimuth, what we use is we use a sentence encoder to compute semantic similarity between each pair of utterances. So we've heard about that in the talk before. And what we do with this analysis is that we try to detect what we call class overlap. So based on the neighbors that are most similar to each utterance, we see if there are some classes that do overlap a lot semantically, and this is what we show in that graph. So if we just look at the class's name, we can already kind of understand, right? So this is share location that overlaps with current location. What is your name? That overlaps with username, but also overlap with change AI name, change username. There are kinds of a lot of intents that relates to the name of someone. So you can go through that plot and try to understand a bit more the overlap, and we'll see later on is that overlap is a problem, because it might not be a problem. Sometimes classes overlap semantically, but the model can easily distinguish, but sometimes it's harder for the model to do so.
Right, it's natural that there might be semantic overlap in your classes, and you want your model to handle that, but at the same time, it might be too hard, or at least you should know that it's too hard before you ship the model. And I think the last area then will be problematic examples. Right?
I have so much more to say about class definition.
Okay,
hold it there. So I just here kind of shown an overview of the class overlap, but let's go a bit more into details, right? So in Azimuth, we have this notion of smart tags, and I'll explain it briefly because it's core to a lot of our analyses. So smart tags, just think of them as regular tags that we assign to specific examples in your data set based on some function. So some smart tags are smarter than others. So for example, we compute high epistemic uncertainty, and we assign a smart tag to all utterances which has high epistemic uncertainty, because we do believe this could be an interesting thing to discover. And others are maybe a little bit more trivial, such as tagging long sentences, short sentences, maybe utterances that misses a verb, and so on. But the smart tag I want to talk about now is in the dissimilar category. So I haven't mentioned it, but smart tab are grouped into families.
I'm sorry, can you just make it a bit bigger for the people in the
Ooh,
back? If you're able, if you're not.
That's a good test. It works. You're testing the demo live. This is mean. but yeah, it's a good thing. That's better. Perfect. So the smart tag I want to talk about is in the dissimilar family. And these are all smart tags that relates to the similarity analysis. So using the sentence encoder to compute some interesting stuff. The one I want to talk about is the conflicting neighbors train. So if I click here, what it does is that it filters the right panel here. So here I look at all the utterances, which so these utterances, their neighbors, they belong to another class. So let's take an example. So the first one, the utterance is, how do I ask about the weather in Chinese? The label is translate, but the prediction is weather, right? It's understandably so. I missed that word. If we look at the most similar example in the training set, so here, this is where the zoom in is not so great. We only see 2 at a time, but bear with me. Tell me how the weather is from the weather class. Tell me what the weather is like. Here, a Chinese one. Please speak to me in Chinese, but it's changed language. What's the weather looking like, and so on. So if we look at the top 20 neighbors, most of its labels belong to another class and then translate class. So this is why we tag to this utterance the conflicting neighbors train smart tag.
So that means that perhaps the label translate is just too broad, right? Is overlapping with other labels, and therefore we might want to break that label or change it something. Right?
Exactly. So that smart tag is useful to explore utterances like this who might hint at problems in your data set. If I go back here, so in this view, this is what we call the prediction overview. So we were looking at the raw data here, but this is a view where we aggregate that data in some useful way. So this is a confidence histogram. And we show here the x-axis is the score of the model, so the confidence score. And in the bars, we show the number of utterances that fall into each of these confidence gap. The different color here represents what we call the outcome of the prediction. So the light green means that the predictions were correct. The dark greens mean that the predictions were also correct, but they belong to the out of sample label, so you might not care as much about them. Out of scope. I always say out of sample. Out of scope. Thank you. OOS. Then way I'm safe. Below the axis is the incorrect prediction. So the red are really incorrect, and the orange, they are also incorrect, but instead of predicting the wrong class, the model predicted the out of scope class. So it's a bit less bad, if I could say, than predicting entirely the wrong class.
So for those who don't know, the out of scope class is if you're trying to predict intents, and well, you don't know what this intent is, well, you'll call it out of scope or no intent. So it's better than predicting something wrong if you just say, I don't know what intent is.
Thank you. So if I look at the confidence histogram right now on this conflicting neighbors train smart tag, which I just talked about, you can see actually the model is not performing so well if I compare with the overall performance across the data set, right? So it really shows that that smart tag is able to find some utterances that are more interesting to investigate instead of like just looking at errors randomly. Just before I finish on the class definition, I just wanted to show that here in this plot, we show for all the label how many utterances were tagged in a given smart tag grouped by family. So here I was talking about the dissimilar family. And so if I sort here, I can see what are the top labels which has which utterances are the more tagged according to that similarity family. So the ones that are more problematic in terms of their neighbors. So it's interesting because here we have definition, and this is a class where you can basically ask to define anything, like what does a chair mean? So of course it's a very broad intent, so we can understand why there's a bit of a problematic in terms of its neighbors.
So if I'm trying to assess whether the data set is well constructed, I would go to this graph, sort it by dissimilar, and at least see is there conflict in the training set semantically. Right?
Exactly, and the color here shows you the actual performance. So the same color I showed before, so you can already see here. We can see here there's a class, a restaurant reservation, which is problematic as well.
Right. For 150 is a lot of classes. If there were fewer, it'd be easier. But I get the point.
Yes.
So now we can move to problematic examples,
now I'm ready.
right? Okay, so class definition gives you a sense. Maybe you have to work with your classes. You got to go back to your domain experts. You got to go back to your annotators, perhaps, before you start blaming the model. Right? But now there's a whole other category of examples that are a little strange that I want to find out. How do I do that with Azimuth?
So we already kind of started, right? When you're looking at the conflicting neighbors train, you can already sometimes see, mislabeling issues, right? When their neighbors is very far from itself, it might be just a mislabeling problem. So that's part of it. But here we can do a bit more. So we have an uncertain smart tag family here. And what we do is that if the model that you provide to Azimuth has dropout in it, we calculate from it the epistemic uncertainty for each individual utterance. And if the epistemic uncertainty is high, so we define a threshold, we tag it with this smart tag, which is called high epistemic uncertainty. So looking at this example can help you identify what utterances might be noisy, outliers, or again mislabel
So in that case,
problems.
since my model has this orange sort of color, that means that I'm predicting out of scope for those examples, which kind of makes sense, right? Because if it's out of scope, that means the model is not sure where to place them, so they're just putting it on out of scope, right? So this smart tag kind of surfaces that.
Exactly. Another way you can detect some problematic samples is perhaps through the extreme length smart tag family, and this is where we tag either extremely short or extremely long sentences. It might not be problematic in some use cases, but it might in others. So here you can see what are the ones with the most utterances with extreme length, and also the performance with the color. We see no here is one with very short utterances, but basically when the person says no, the prediction should be no. But we see the model struggles a bit with that class. Also, just before we change of category, Before being here today, I actually did a bit of analysis with the smart tags that I just talked about, and I was able to spot a few mislabeling issue. So what I did is that here in Azimuth, for every utterance, you have a field where you can propose an action to improve your data set. So for instance, as you go through it, if you do find some mislabeling issue, you can tag them as relabel. You can also, if you think that maybe the training set is too far away, you can say, you should augment this with similar examples. You can decide on the spot that maybe you should define a new class, or maybe merge the two classes, if, the label and the prediction, if they are maybe too close to one another. Can remove, and so on.
Okay. So I guess if I tag them with augment with similar, I could run some back translation, right, with a high similarity threshold, and maybe that will address that problem, right? Cool.
Just before I close, there's an interesting problem here in that it's a known data set, right, Clink? But there are 4 examples where the label is change accent, but actually it's a change account that it should have been. So it's probably like an autocomplete problem from the labeler. There's 4 examples like that were found with the conflicting neighbors train smart tag.
Okay, so now I can go back to my linguist who helps me create my data set, and I can say, here's a report. Let's go through it carefully, right? Cool. Okay, so now, the data set is okay. I mean, it has some issues, but I have a pretty good model. It's a distilled BERT fine-tuned model. It's not a super hard task. It's 90% globally accurate. What can you tell me about this model, right? So I guess first, let's look at some data subpopulations, right? 90% overall, but what does that mean if we start slicing and dicing the data set?
Exactly. So in this table, you can see that you have different types of subpopulation you can use. So all the smart tags that I talked about are here, but also the label and the predicted class or obvious subpopulation. So here you can see different metrics, and we compute their score, both for the evaluation set and the training set as well. So it can be interesting in the training set, because if the model struggles on data it has already seen, maybe it's telling something about either your data or your model that should be fixed. So for instance, in the training set, if I sort by the F1 metric and I look at the top ones, I can see that what is your name, change username, change AI name are kind of at the top. They're not doing so great for the training set. And these are examples we've seen before from the class definition, right? We know there's a lot of semantic overlap here, and it doesn't seem like the model is doing so well. If I go back to the evaluation set, I can show the performance on different subpopulations. So partial syntax, something that we compute for every utterance again. So if an utterance is missing a verb, an object, or a subject, we tag it with that smart tag. And we can see from here that the model is actually struggling with utterances that are missing a verb. So we are often predicting the out-of-scope class for these ones. And in terms of extreme length, so the model is performing a bit worse on short sentences, with 82% here are correct, and long sentences it's actually better than average with 93%.
Okay, so this is going to help me then focus where I can put effort to bring that 90% high to 95 or something, right? Because sometimes you have no idea where to start when you're trying to improve your model. So this is a good dashboard. Thank you.
And from here, if you want to explore further the errors, you can click on the row, and it brings you to that space that I've shown previously, where you can really explore further yourself the data and the metrics and so on. And another thing I wanted to show you here is that there's also a confusion matrix that we display that also is a type of subpopulation if you want. It's an intersection of every pair. And the confusion matrix on 150 classes is very big. But what we do that's interesting here is that we do order the rows and the columns in a meaningful way so that classes with similar confusions are one beside the other. So here we can see little clusters of confusion, right? So redeem rewards balance, reminder, to-do list, change accent, freeze account. This one is actually due to the mislabeling mistakes that we found. Right. So it's not a real confusion. Yeah.
Cool. Okay, so now if I guess we can move on to annotation artifacts, yes. Right? So just to repeat again, annotation artifact is a pattern in your training data that your model will exploit to learn a heuristic. And you might think it's doing the right thing, but it's actually learning the heuristic instead of learning, in this case, linguistic capability to do the right prediction. So how can I try to find that? I know it's hard. How can I do that with Azimuth?
So one way you can do it is using the word cloud here. I haven't presented it earlier. So what we do here is, in fact, let me show you this first. So you may have seen already the yellow highlighting earlier when I was showing the utterances. So this is actually saliency maps. So what we do is that we use the gradient of the model to infer what the model is looking at when it's making its prediction. Okay, so using these words, we do a word cloud and we show what are the most frequent words that are also salient, according to the saliency maps, that comes up for correct prediction and for incorrect prediction for any slice of the data that you want. So this can be very powerful to understand if your model struggled with a specific word, but it can also be useful to try to detect annotation artifact. And let me show you an example that I think is very cool. So in the label accept reservation, if you look at the word cloud, it's pretty fascinating. There's just one word in each. And every time the model gets it right, there's an S, right? It's plural. And every time the model gets it wrong, it's singular, right? It was like, wow, this is very, very, very clear. If we look at the training set, reservations is almost always plural. There's reservation 5 times without an S, but it's very.
Okay, so hold on. So in that class, in the training set, the plural form is almost always present. But in the validation set, the plural form is not always present.
Let me show you. If I actually look for the word reservation singular, I added a space at the end. If I look here, this is in the filter, we also show the distribution of the values according to the different dimension here. So imagine that these bar here is just the sum of all these bars in this graph. Mm-hmm. So we can see that the reservation singular is actually present in confirm reservation, cancel, restaurant, but the class we were looking at, which was accept, is barely even there in the training set when it's singular.
Okay, so my model, it hasn't learned that reservation is part of accept reservations.
Maybe it learned that if there's an S, then it's more likely to be this one, but if it's singular, it's more likely to be in the other ones.
Okay. Okay, so that's pretty cool. So how do I fix that then?
I mean, data augmentation is the obvious answer, right? Trying to maybe to look at your training set and try to add examples, or maybe looking at an example, we could look at them now, but looking at this example, maybe they are always they would be in accept reservation, but maybe there's always written in the same way, right? So maybe it's always like, do this restaurant accept reservation? You know, do they take reservation? Take reservations, right? So maybe there's not enough variance in the way your sentences are written for that class.
So in this case, comparing to what was explained before, the innovation was just add more data, a little blindly, right? You just add more data that is similar, but I guess in this case, we want to target, right? It's targeted data augmentation to address specific issues.
Exactly.
Okay, so that's for annotation artifacts. Now, Rivero and colleagues came up with that paper. We think it's really amazing work. I know that my customers get very annoyed when just by having a typo or missing punctuation, the model predicts a different class. And although it doesn't happen very frequently, when it happens, it annoys them, and then they open a task, a customer task, and I have to address it. So how can I find that out in a cheap way before I actually deploy my system?
It almost looks like I know what you're going to say. I'm always ready. So we do have some behavioral testing in Azimuth. So when you launch Azimuth, we for every utterance in both the training set and the evaluation set, we do some tests. So we perturb in different ways these utterances. So we have we introduce typos. We play with the punctuation. We introduce neutral words. And what we do is we compare the new prediction with the original prediction. And when it's different, we say that the tests fail. And so these failure rates here represents the number of tests across your evaluation set and your training set where that new prediction was different from the base one.
Okay. And anybody can add more tests, this style of checklist to test many more things besides just typos or neutral words, right?
These are all Python functions, right? So I can, as long as you can write it as a Python function that takes an utterance and produce the new utterance, then you're good to go. And
it's open source, so anybody can contribute. Okay, I think we're yes, I think we're running out of time. The high systemic uncertainty, you already showed it, but is there anything else you want to show before we open up for questions?
Let me look at what's left. I mean, we can discuss a bit the confidence histogram here. I just wanted to point out that the confidence, actually, the top confidence is around 90%, which is not so high, right? So the model is generally underconfident here. So in Azimuth, you can put more than a pipeline. In fact, let me show it here. And I actually changed the temperature scaler in Azimuth to test it. And with a new temperature scaler, actually the model is way better. So if you look at the ECE now, it's pretty close to 0. So you can test that in Azimuth. We also have a comparison mode where you can compare the metrics across your pipeline if you want to on any dimension that you want. How much time do I have? 1 minute. Oh, this is painful to choose. You'll need to join our Slack. Yeah, maybe we can just finish.
Yeah, that's fine. I guess what the comparison is useful if you have to ship a new release and you want to compare with the old release on your same data set. You can easily see where you're improving or maybe regressing. And
I'm looking for my PDF. Where is it?
Yeah, many of the contributors are here.
We have two. So Joseph and Fred here are contributors as well. So this is the great team working on this. And we're hoping this can be a success story, right? We want contributors, we want people to engage on this conversation. We're really interested about the topic. So please star our repo on GitHub. This is our boss knows that this is successful. So please star. That way I'll get a raise. And join our Slack, please. So it's a new Slack account. There's barely anyone there apart us who just talk amongst us. So please join our Slack. It would be great to engage with the community. And we also got accepted at ENLP as a system demo. So we have a paper. Where's the paper? We have a paper that will be published in December. So please check it out. And that's it.
Amazing. Thank you, guys. I've seen probably what was the V0 of that.
Yes, you did.
You've come a long way, and I'm really, really happy to see you guys present today. So we're opening it up for question. We have about 10 minutes. There's a mic in the front. Don't be shy. And maybe I can start by asking you, that's fantastic if you do classification. If you don't do classification, what do you do?
Well, so we're looking into other tasks, right? Like I spoke about summarization. I mean, it's not very obvious to do other tasks. And you can see how much thought you have to put into just one task. So I would open the question to the community and help us actually increase the number of tasks that then everyone can use because it's open source. But for summarization specifically, you can try to like I said, compare factual, right? Are you just think it's a different kind of way to testing. Are you being factually correct? What is the length of your generation? What is your model looking at when it's generating each token? There are things that the one can do, but it's very specific.
So I'm not a big fan of just putting more data in your model because of the sake of just putting data. So I was very happy and interested when you show this example, when you say, well, we can see that we don't have enough of data in the singular form of a word. In that sense, have you have thought or are you aware of some linguistic variables that you can use that may help you to characterize the text that is needed to be included in your models?
Linguistic, you can.
Well, there is some variables, for instance, nominalizations that can characterize more formal text, public verbs, cognitive verbs that express the thought of someone who is talking. Those are linguistic variables that we have in corpus linguistics. Maybe the name of that, one of the authors, very well known, is Douglas Bieber. And there's a big list of, I think it's 2045 variables or something. But I think it will be really good if you put in the next version something.
Yes. So perhaps have smart tags that detect some of this. So you can help us.
I will contact you. That.
Yeah, join our Slack. That's great.
Thank you.
First of all, thank you so much for your great presentation. I think it was really fantastic in terms of the subject and of this presentation both together. My main question is that all your done work is mainly related to the NLP and text data. And as I understood, it's kind of related to the MLOps or kind of after type of the monitoring when we see the errors about the prediction. Could we kind of extend your kind of approach to that part also, or kind of just before, because you were mentioning it's kind of sometimes before deployment, but I think it can be extended to the part of the after monitoring because we were mainly working with the error analysis after monitoring also. And this is my first question. And the second one is that could be extended to the numerical data also because all the done works that you did, it's kind of sometime kind of I also have it for my work for the part of data augmentation, kind of the problem that you had for the imbalanced data. But mainly I was kind of working with the text. My question is that could we kind of extend it to the approach that you are mentioning for explanation, different kind of data strategies that you applied, could be extended for the numerical data also, or something that it's under the research for your side?
So I'll take the first one, you take the second one.
Perfect.
So definitely, you don't stop working once you ship the model, right? Actually, your work just starts once you ship the model. So some of these techniques, we are working to integrate them as part of our monitoring. No, it's not exactly the same tool, right? You kind of want to get alerts, right? You want to get automatic alerts and get some data, triggers the alerts. So we have some work in mind to use some of these tags and ingest them into our monitoring tool. It just wouldn't be the same kind of tool, but the same principles apply. And I'll let you take the second question. Yeah,
for the second question, the answer is absolutely as well. So we did focus on NLP because ServiceNow, this is where we work for. This is all, like all of our AI is pretty much NLP based. We did start this project way back on vision problems and also time series. So time series is not tabular necessarily, but it's a bit closer to tabular data, right? So it was forecasting. But I do think that a lot of like our proposed approach with those squares, I don't think that's NLP specific, right? This is ML specific. And for sure, how you discover an annotation artifact is very different if it's not text, right? The word cloud only works with text, but I do think the same reasoning apply, trying to understand like what your explainability method are saying. So I do think it's feasible. Have we done it in Azimuth? Not yet, but like if someone, knock at our doors and say, I want to implement this for tabular data, we're going to welcome you, so it would be great.
Perfect, thank you so much.
Of course.
Great, great product and great presentation, thank you. Two questions. The first one is fairly quick. How long does it take to do all the analysis?
It's a good question. So it depends of your machine. It depends if you have GPU or not. It depends of your data set size and your model size. This is a big model and a big data set, so I think it takes an hour or so with one GPU, I think, for this one. But if you just have like a few hundred example in each split, you can run it on your computer CPU and it will maybe take 20 minutes or 15 minutes. It really depends on the data set size.
Wonderful.
Depends on your base model that you're evaluating as well, I guess, because that's what you're running inference on, right?
Exactly.
And we're also allowed to customize what you want to run. Here we run everything. But say you don't really care about epistemic uncertainty because it's expensive to run multiple. You can just disable that via configuration.
Yeah, we explain all of this in our documentation, by the way. So if you want to go take a look at our documentation, we explain the config file where you can really set up your app and decide on the different data set you're going to use, the thresholds, and so on. So
excellent. Second question is about the smart tag. I see some cases where it didn't tag everything. Is there some limitation to that?
I'm not sure what you refer to. That sometimes they weren't any smart tags.
Yeah. Or I see in one of the examples you gave, forgot for which one, for the short sentence and long sentence, yeah. they are like no tag, but that's like 2,000 some examples there, whereas the short sentence and long sentence have 120, 100-ish.
It's like an exclusion filter, so it's if you want to filter all the utterances that don't have an extreme length tag,
Okay, so it tags everything. Just there's a tag called.
Exactly. So some examples we will tag with one or two, some with none. I mean, we try to tag everything so you have everything available. Yeah.
All right. Thank you.
Thank you.
Hello. So my question is, what are the main contexts that this tool was basically built for when it comes to text classification, and what's also the scale that it's built for?
The context, you mean?
Like the types of tasks it's usually best at analyzing.
So this is limited to text classification.
Right.
So anything, sentiment analysis, intent classification, anything that you classify text to a number, right, to a class.
Got it. And what scale is it generally built for of data?
Well, it depends on your resources, right?
Okay.
Because if you have limited memory, well, you cannot fit a large data set. If your model is GPT-3, well, you're not gonna fit it in your laptop. So it really depends on your hardware. We think it scales pretty decently, given what it's designed for.
Right.
So yeah.
No, so if you're using it like a large organization with millions upon millions of basically rows of information, it would still be able to give you very good results for the analytics.
Millions, I'm not sure. I mean, if you have labeled data that has millions, it's not very common, right? Like labeling is expensive. So, but thousands, tens of thousands.
Okay.
Yeah, here we have 3,000 in the evaluation set, and I think 10,000 in the training set. So that's a big one.
Okay, got it. Thank you.
Right. Excellent presentation, so thank you for that. And also I'd like to say thanks for the excellent question about monitoring use cases, so kind of post-deployment. That was exactly the question I was about to ask. Kind of related to that, so this is a tool that's designed pre-deployment, right, to do investigation. From a business point of view, do you provide any reports, instruments for someone like a decision maker who basically signing off on the deployment? Because you look at the plots, you look at the error rates, what happens after that? How do you communicate to department directors and whatever that we're good to go with the deployment?
Yeah, that's a great ask. We've thought about certainly having an export function where we can have at least some sort of a PDF version, because this is really an interactive tool, right? And we really have in mind here a data scientist as a main user, right? It's quite technical and you can really explore in any way you want. So for sure, if you would want to support that use case, we would need to think a bit about our UX, right? Right now it's really you can go in any direction, maybe in a more guided fashion of checks. So we could.
Now, one way that we want to use this is when we produce something like a model card, right? We want to say there, look, there are these limitations that we have identified with this tool. Now, it's not an automatic thing, here's the model card, but it can be used for that, right? In the model card, you say, look, we have tested with this tool, this is what we found.
Yeah.
And related to that, do you envision Azimuth to be integrated with some CI/CD processes? And what some examples that I'm thinking about right now is you showed that you have some tests, almost like unit tests for a model, where you introduce perturbation, some punctuation, and you see the error rate. I could see that in some use cases, people might want to train their model, and if that error rate is below a certain threshold, just go ahead and deploy it. You see that as more of a command line experience rather than a UI.
Yeah, we see where your background, right? So a bit more MLOps. Yeah, it could for sure.
Yeah, so definitely, right? Traditionally you have a report that you see every day. How many bugs do I have? And is it going down? Something like this can be integrated into that, right? At least robustness. I can see every day. Okay, this person shipped this feature. How has it changed? So yeah, it can definitely be integrated into that.
Yeah, and metrics by subpopulation too, right? You modify your data sets, you get better at long sentences, but do you get worse at short sentences, for example? So being able to go at a more granular level with your metrics would be useful.
Okay, excellent. Thank you.
That will be the last question.
Oh, okay. I was I thought that was You're fine. Okay. My question would be, Obviously, you build this tool for AI practitioner, but what would be the features that are the more accessible for with less expertise, less experience, and then like to go just from there? And because like obviously we want adoption for this kind of tool. So what would be like the steps towards that?
It's a good question. I think the holy grail would be to be able really to propose some actions that someone should be doing, right? So being able to say like, these are the examples that you should be relabeling, and these are like the things you should be looking for. But it's a hard problem, right? Like going from insights to really like recommendations. So I think that would be like kind of the way we should move forward if you want to make this more accessible to people who don't know ML so well and are just kind of trying to, either sometimes there are people providing data set, right? So they want to clean their data set, but they don't understand really like what annotation artifacts are. So it's a bit hard for them to be doing the types of like filtering I've been doing and looking for them. So ideally, the more we can move towards automatic, I think would be great, but yeah, I'm not convinced it's going to be easy to go there.
The human element is very hard to replace, right?
Yeah.
The capacity human beings have to compare, to analyze, to synthesize, to link, it's very hard to do that still.
But I think the smart tag concept and just looking at the raw data, that speaks to everyone, right? So at least making this accessible for people to be able to just search as you would normally search on your computer, just being able to do that, I think this is already a good way to bring less technical people to the table so they can discuss. Even linguists, right? People who might be like really language experts can contribute here and say like, oh, this this is problematic for that reason, or we should relabel and so on.
Thank you.
Thank you so much, guys. Thanks for the good questions, everyone, again.